Any rotating body exhibits gyroscopic phenomena. The Earth is a gyro, spinning about the imaginary axis between the geographic poles. A child's top is a gyro, and so is an aircraft's propeller when it's turning, especially at high RPM. The rotor which forms an aircraft instrument gyro may be little more than an inch in diameter, spinning at perhaps 25,000 RPM. Gimbal rings are the supports for the rotor of a gyroscopic instrument. Gimbal rings are sometimes just called gimbals. This diagram shows a spinning rotor mounted in two gimbal rings, the outer one being supported by a fixed frame. The rotor itself is a metal disc which rotates about this axis, usually called the rotor spin axis. The rotor shaft, or spindle, is supported by bearings in a ring called the inner gimbal. The inner gimbal is in turn supported by bearings mounted inside the outer gimbal, which can rotate on bearings in the frame. If an external force, or more correctly torque, is applied to change the direction of the rotor axis, the gyro resists angular movement in the plane of the torque applied, and instead moves in a plane at right angles to that of the torque, the resulting movement being called precession. The rule of precession states that the gyro will precess in a direction at 90 degrees to the applied force, measured around the circumference of the rotor in the direction of spin. The force applied appears to have moved 90 degrees in the direction of spin. A spinning rotor maintains its axis pointing in a fixed direction in space, unless it's subjected to an external force. This property is called rigidity in space, or gyroscopic inertia. There are three factors which affect the rigidity in space of a gyro. They are the rotor mass, the effective radius at which the mass acts, and the speed of rotation. To increase the rigidity of air-driven gyros, the rotor is manufactured from brass, and to increase the effective radius at which the mass acts, the brass is concentrated around the rim of the rotor. Finally, the higher the rotational speed of the gyro, the greater its rigidity in space. If a gyro has only one gimbal ring, with consequently only two planes of freedom, it can be adapted for use as a rate gyro, which will measure a rate of angular movement. If the gyro frame is rotated in the plane in which the gyro has no freedom, the rotor will precess, unless restrained, until its plane of rotation coincides with the plane in which the frame is being turned. If this precession is restricted by a spring, as shown in this diagram, the resultant tilt of the rotor will be a measure of the rate of angular movement of the instrument. This instrument incorporates two measuring devices, both indicating on the same instrument face. One of these, the rate of turn indicator, commonly shortened to turn indicator, uses a rate gyro to measure rate of turn about a vertical axis. The other, the slip indicator, is a very simple pendulous device which is used mainly to show whether or not a turn is balanced, whether the angle of bank is correct for the true airspeed and rate of turn, and if not, to indicate the extent of slip or skid. The turn indicator employs a rate gyro, which, having only one gimbal, has freedom about only two axes. There is, of course, complete freedom of rotation about one of these, the rotor spin axis, which in level flight lies athwartships. There is restricted freedom about the longitudinal gimbal axis. There is no freedom about the aircraft's vertical axis, so any torque applied about this axis, as in a turn, will cause the gyro to precess. Suction and electrically driven types of turn and slip indicator are available. With the former, an engine-driven pump, or Venturi tube, is used to apply suction to the instrument case. Replacement air enters via a filter and is directed by a jet at buckets cut in the periphery of the rotor. The rotor rotational speed is low compared with that of the directional gyro indicator and the artificial horizon. This is because the gyroscopic property of precession is used to measure rate of turn, and so a high gyroscopic rigidity is undesirable. A damping system fitted to the gimbal reduces oscillation. This may be the piston-in-cylinder type or an electromagnetic device. Stops limit the ability of the gimbal to tilt to an angle corresponding to a turn of about 20 degrees per second. If the suction to an air-driven instrument is inadequate, which can happen as a result of either high altitude, or with a choked filter, or even perhaps a leaking suction tube, gyro rigidity will be lowered as the gyro is under-speeding. Consequently, the secondary precession needed to equal the aircraft turn can be generated by a smaller secondary torque. This reduced torque will be produced by a smaller angle of gimbal tilt, and this means that the instrument will under-read the turn rate. Alternatively, if the gyro were to overspeed, by the opposite process it will over-read the rate of turn that is being achieved by the angle of bank applied. It's desirable that turns should be properly balanced, with no side slip or skid. The slip indicator gives a direct indication of the state of balance of the turn. Early types of slip indicator employed a simple metal pendulum suspended in the instrument case, its oscillations being controlled by a piston-in-cylinder damping device. The modern version, a sketch of which is shown here, is usually a ball-in-tube inclinometer. This comprises a solid ball in a curved tube containing liquid which damps out the unwanted oscillations. The heavy ball behaves like a pendulum, with the center of curvature of the tube acting as the effective point of suspension. The turn coordinator is an interesting development of the turn and bank indicator. The primary differences between the turn and bank indicator and the turn coordinator are in the setting of the precession axis of the rate gyroscope and in the method of display. The gyroscope is spring-restrained and is mounted so that the axis is about 30 degrees with respect to the aircraft longitudinal axis, thus making the gyroscope sensitive to banking of the aircraft as well as to turning. A turn is normally initiated by banking the aircraft. The gyro will precess, and this in turn will move the aircraft symbol to indicate the direction of bank and enable the pilot to anticipate the resulting turn. The pilot then controls the turn at the required rate by alignment of the aircraft with the graduations on the instrument dial. The rate of turn will depend on the instrument in use, either as a rate 1 turn, 3 degrees per second, or any other rate dependent on instrument design. To achieve a balanced rate of turn, the ball still has to remain central. The annotation "No pitch" information on the indicator scale is given to avoid any confusion regarding pitch information which might result from the similarity between this presentation and the presentation of the artificial horizon or attitude indicator.